Welcome back to another video. We're talking about systems of linear equations. As a reminder, when we talk about solving systems of equations, we're looking for a single solution that solves all the equations in the system. So in general, a system of linear equation will be a set of more than one equation, two or more, and we're looking for solutions that'll solve all the equations simultaneously. How do we do this graphically? Well, the graphical solution is just one of a few different ways of solving, but when we do this graphically, what we're looking for is we're looking at the graphs of the equations and looking for a single intersection point. When the graphs intersect, we know that we're hitting a point that is on both graphs. Like in this case, we can see here in this example, this point here where they intersect, the red and the green line, that point will satisfy both of these equations that lead to these graphs. So how do we do this? Well, let's look at an example. And the idea, as always, is that we're looking at it when we're graphing an equation. What we're doing is we are looking at the equation as if it is a function, where we have an independent variable, usually x. In this case, it's w, and I'll explain why in a moment. And we have a dependent variable, f. So independent and dependent variable. So when we look at it in that form, we basically can look at it as a function, and we can graph the equation where one of the variables is in the y direction and the other in the x direction, and they behave as a function. So let's look at this example here. We are looking at a baking example. To bake great bread, bakers follow a strict flour to water formula. So it's a ratio of water to flour or flour to water. And typically, a typical formula would be flour to water equals a ratio of 5 to 3, or the flour equals 5/3 times water. So that's what it means when we say that we're following a water to flour ratio. And that equation basically says if we write our flour as our dependent variable f equals 5/3 times our independent variable w here. And that is exactly what we have in this line here. At 0, when we have a 0 amount of water, we also have a 0 amount of flour. And if we're looking, at 6 ounces of water, well, 6 ounces of water will correspond with 10 ounces of flour. So that is this red curve, this red graph here follows the equation for the ratio of water to flour, where we've written it as a function. Now, when we bake bread, we want to know the size of bread we have. And the question here is how much flour and water are needed for a small loaf, 1 pound, and a large 2-pound loaf. So basically, we're given another equation here, equation that has to do with the weight of the loaf, the size or the weight of the loaf. And if we look here at the blue equation here, what we're saying is that for a small loaf, the weight of the flour plus the weight of the water should equal 16 ounces, which is just 1 pound. We can write this in another way, right? But if we subtract the water from both sides of this equation, we get F, flour, equals 16 minus water. Okay, and so this is going to be our second equation, again written as a function of the dependent variable flour, as a function of our independent variable water, W water. And that is this blue graph here. So because we have a negative sign in front of our water, W, the graph goes down as we increase the amount of water. So this blue line here is our second equation, and I'll highlight the second equation in blue here so that we remember that that is the graph of that equation. Now, what we have here is, again, we're looking at the intersection of the two lines because we're looking for a single ordered pair, okay, WF, that will solve both equations. And the only ordered pair, and I wrote it as WF because W here is our independent variable, similar to X, and F is our dependent variable, similar to Y. And we're looking for that kind of ordered pair that'll solve both these equations. But we know that the equation, all the ordered pairs that solve these equations are on these two graphs, right? The blue one solves the blue equation, and the red one solves our, well, our black, or let's highlight this in red here as well, our red equation. So our solution is right here at the point where they intersect, which is just water equals 6 and flour equal 10. So we have 6, 10. And we can check that this point indeed solves both equations. So we can start with F equals 5/3 times W. That's our first equation for the ratio. If we put, instead of F, we can use 10, right? That's our water, our flour, equals 5/3 times 6, question mark. And indeed, 6 divided by 3 is just 2, so this equals 10, and so we get the correct answer. I included also the equation here, or the graph, for our green formula, right? Our green problem, which is the 2-pound problem. So in this case, I'm going to erase some of this so that we have a little more space and order. But basically, if we look at the 2-pound problem, the weight of the flour plus the weight of the water equals 32 ounces. And again, we can subtract W from both sides. And we get F equals 32 minus W. And that is this graph here, this green graph here. And again, we're looking for the intersection of the red graph with the green graph. The red graph is our ratio of water to flour that never changes. We always go by that rule. But when we're looking at a 2-pound loaf, now we have a new equation for our 2-pound loaf, which we wrote out as an equation. Again, F here, flour, is the dependent variable, which is like our Y, while W is similar to our X, our independent variable. So where do these two intersect? They intersect right here. In water, we have 11 and 12. Each one of these squares is 2. And our flour is 20 here, so we have the point 12, 20. Okay, let's check this. So again, we start with F equals 5/3 times water. Let's put 20 for our flour equals 5/3 times water, which is 12. And 12 divided by 3 is just 4, and this indeed equals 20. Now let's also check our second equation, right? F plus W should equal 32. So we have F, we said, is 20. W is 12, right? We're getting that from this solution here, the second solution. 20 plus 12 equals 32. So we see that this result solves both equations simultaneously. We have the same ordered pair solving both equations. So this was a demonstration of how you graphically solve systems of linear equations where you're looking at the intersection of the graphs of the equations. The important things is to consistently identify an independent variable and a dependent variable, and use that identification to write out the equations as functions of the dependent variable of the independent variable, and use those graphs then to look for the intersection. So take a look at the other methods for solving systems of equations. They are in the same playlist. Thanks for stopping by.